But that's what's great about being a scientist is you're paid to learn your whole career. Both my parents did not go to college. My father was a fireman, which actually it's a very technical occupation where you have to know a lot of safety and you have to understand the physics of fire and the physics of mechanics. And I'm sure if he would have had the educational opportunity, he would have gone to college and been a very successful engineer, for example. So he really thought that way. And my mom was a homemaker. She stayed at home and took care of us. So we came from a very typical middle class, but not necessarily one with an academic background. But they did really emphasize education and working hard in school, and very typical kind of family background where in the end both my sister and I went to college, and we were it was kind of expected to do that, but not really forced upon that. And I was very good at math and science. I always enjoyed that. And my parents, helped me do that. They bought me various science kits when I was growing up, including a mechanical computer when I was not maybe when 12 or 13 years old, where you put it together and you did. I remember that was kind of interesting. The other really important thing they did, which I kind of give as a recommendation for parents to think about, which was very useful for me becoming a scientist, is when you come home and you're sitting around the family dinner table, the parents often ask, "Oh, well, what did you do today?" And then the children kind of roll their eyes and they don't say it because it's such a bland question. So, what my parents did all the time was to ask me if I asked any questions during the day and, what were the questions and the like. And I think that's very good training for a scientist to always be asking questions and to thinking about that and trying to understand and not to be shy because it's kind of hard to ask a question. But if the parents are encouraging you, all the time to ask a question, that's good. So when my two boys were growing up, we tried to encourage that. And what was good is being a physics professor, if they ask anything about the natural world, I can go deeper and deeper and deeper. And most of the time, get to where they wanted to do. And if it was in the biology realm, that's my wife's background, she could do the same. So we kind of had science covered and was able to do that. And yeah, I'm happy that our children had a good background that way. And then, so, I did well in math and science. And then I think the big event for in high school was I got to take a physics course in high school and really loved it because it put the math into all the kind of physics I had understood doing things. My dad was always building projects in the garage. I was helping him. I had little projects. I knew how to build things by watching him, and he had a kind of an intuitive view of how physics worked, sometimes, very simplistic, but he certainly thought in first principles. And yeah, getting to a physics class and having someone explain the mathematics to you was great. So I love physics. And then I, went to UC Berkeley, which was great school. At 18, I was being taught by some of the best physicists in the world on how to do physics properly and really enjoyed the challenge at the university. So, a big moment for me was taking the high school physics course. I had kind of intuitively understood a lot of the physics from building things with my father and watching him build things and explaining in a simple way. And then in the high school physics, I just learned the mathematics behind it in a systematic way, of course, in the way they taught physics. It just made a lot of sense. And it was actually kind of easy to study physics for me. I know most people have difficulty studying physics, but for me, it was just putting mathematics behind and structure around something I already felt and knew. So I had the good fortune of taking solid state physics from John Clarke for my senior year. And I really enjoyed the class. I really enjoyed how he taught it and his very clear, systematic way of doing it. And then, part of the class, I think I just started asking him questions about what he was doing. And because of what he was doing, I decided, when I applied to graduate school, to go to Berkeley and to join John's group. Now, what I liked about John's group is that he was measuring quantum noise coming from quantum mechanics in these electrical devices. And what kind of spoke to me is, first of all, my hobby was electronics. I was pretty good at it. And thinking about looking at this macroscopic quantum phenomenon in these devices was really fascinating. And also, as a student, you're learning quantum mechanics. It's this amazing subject that's still a bit mysterious, and by doing this, you could then study it and learn it and extend quantum mechanics in a good way. Now, at the time, I had no idea of the experiment I would eventually do for my thesis that would turn into the Nobel Prize, but I just kind of felt that this was interesting and maybe a new direction. It was very intuitive. Not, I didn't understand the world of physics enough, but yeah, John's a good teacher. He was doing interesting research, electronic devices. Yeah, this all made for a good thesis for me. I naturally, when I started with John Clarke Group, was working by myself, and that was fine, and I enjoyed it, and I was able to make progress and the like, and enjoyed that. But when we did this experiment for the macroscopic quantum tunneling for the Nobel Prize, Michel Devoret came in, and we started working together with John. Now, you're naturally collaborating when you're a graduate student with your graduate advisor. But when Michel came in, I kind of took an immediate liking to him, given that he knew so much more than me. He understood, older, more experienced. He understood how physics was done. He especially understood about cryogenic engineering. We had to make a dilution refrigerator. So, he had the expertise to do that. So I learned a lot from him. And I think, I also contributed. I was an expert at electronics, so I could teach Michelle at the same time. But I would say the most important thing is that Michelle and I would be in the second basement working on the experiment, and we would argue about the right way to do it. And I think we're both pretty passionate about doing it the right way, and we'd get into these arguments. I think some people would walk by the door and wonder what was going on in there. But by arguing, we kind of figured out what the physics was and what we had to do and what we had to build. And I think it was, really important part that collaboration and both honestly trying to do the best job we could to figuring out this experiment that enabled us to do this experiment in a, I would just say, a beautiful way. I really enjoyed how everything came out with the work. Share a memory. It was actually by myself. I think Michelle had gone back to France at the time. And we had gotten the experiment to work, and we were just doing various check experiments on different chips to make sure we do that, did everything right. So I put in a one chip which had a higher current. It was designed for a higher current. And I was just cooling it down and bringing it up. And the first thing we did is we set up the experiment, and you put kind of what was the switching on the oscilloscope. So it's just kind of looking to see if the experiment's working right. And instead of seeing a band of the switching events, kind of as a line on the oscilloscope, I saw three peaks. And those three peaks were the energy level transitions that are kind of the hallmark of seeing quantum mechanics that I describe in the energy level paper. And it's very clearly showing you the quantum mechanics. And immediately seeing on the oscilloscope, I can still see it in my mind, those three peaks. And I knew we had something special here. and that this would be great. And 10 minutes later, I had the computer analyze it, and you could see that it was a very beautiful curve. So that to me was the most definitive proof that we were seeing quantum mechanics in the system, and I could just see it as a raw signal coming out of the experiment. We first did the experiment at 1 to 4 Kelvin higher temperatures, and we did it in this simple wiring method. And the experiment was a complete disaster. It didn't work, didn't make sense. And what happened at that point is we realized we hadn't really understood it fundamentally. So Michelle and I, and John, of course, we sat down and thought about it and understood it was a microwave experiment and that you had to filter it right. We went to the astronomy department and used something called a vector network analyzer and read books about how to design the experiment. And then from kind of that moment on, we built all the elements that we needed so that the next time we took the data, it looked perfectly right. We then built something that got to really low temperatures and all the data came out. So, based on a little bit of confusion and taking data, we then figured out what to do, and then it was just a matter of doing the experiment step by step, and it basically worked at that point. And that was very nice for me as a young student. It's fine to take some data, but you have to sit back and really understand the experiment. And it is very interesting. There's the Nobel Prize in economics, where they talk about the sustained growth. And there's something they talk about called prepositional knowledge. So we had to step back and get the prepositional knowledge to really figure out what's going on. But by then, we just had sustained growth, if you like, in the experiment. And in fact, from that experiment and that prepositional knowledge, it launched the whole field, and other people were able to do good experiments. So that was the kind of the key moment to understand it in that way. In fact, what I always told my students is when we built something and it didn't work, it was, okay, it's depressing and whatever, but there's something here that we have to pay attention to because we learned something. And most of the time that's right, but some of the time it's just to make them feel good because their experiment didn't work and you have to work harder. But all of that's true. The first thing I would say as a researcher is you have to really look for the truth. And that's the number one thing you can do. And part of the problem is when you do research, you can take some data, and if your model, your theory for the data matches the data, it doesn't mean the theory is true. You can only falsify theories in experiment. So you have to be very open to the fact that what you're thinking about could be wrong or could be confusing. And I would say, really looking after the truth, very serious. And that's what we did in this experiment. There were already a few experiments out there. It was kind of murky. And, we really wanted to prove this phenomenon, macroscopic quantum tunneling, absolutely and numerically with error bars. And I would say that's kind of the reason we were successful with the experiment. And that was a good learning experience for me. The thing that worries about me is that there's eroding of trust of the public into scientific results. I think physics, it's a little bit better, but in other fields, it's harder and it's more complicated, say. I think there's some studies saying, half of scientific papers can't be reproduced or, something like that. So, I know in my career, we work very hard to make sure the data's right. And we do a lot more experiments that are never published to check that things are working properly. And in fact, I was looking at some data this morning, thermal conductivity data, and, it didn't quite look right. So, we went back to the people and said, there's a little mystery here. We have to take the data better to make sure we're absolutely clear about that. And I think that's an important job of the scientist, is to make sure you're skeptical of your own data, make sure that when you publish it, you can stand behind it well. So the first of all, I think it goes back to what I talked about earlier. You should be asking questions and making sure that you don't feel intimidated by asking questions all the time. And, make sure you're doing that. And also, as you're looking at what people are doing around you, um, make sure you look for, let's say, little discrepancies in the data, or someone's has a new idea that's very bold. Make sure you're looking out for that, because that could be, a very important result. It may lead to a Nobel Prize, or at least to an exciting career exploring something. Be open to that. But also, it takes a while to learn how to do research well. And I was very fortunate in graduate school, had John Clarke and Michelle teaching me how to do that. And obviously, I learned a lot in my first 5, 10 years on my own how to be a good researcher. And it just takes a while to learn how to do that and to do science at a high level. And you just have to be constantly learning. I'm constantly learning. And for example, right now, I'm part of a startup company, and I have to learn about business and economics and persuasive discussion of what the plan of our company is. I remember I learned in graduate school, I couldn't make these Joseon junctions. They didn't work at all. After months of trying different things, I finally went into the clean room and spent the day cleaning out a vacuum system, which was grungy work. Hated, but it was only an afternoon, a day, and then everything started working. So, don't be afraid to, roll up your sleeves and clean out your system, or do something in order to get it to work. And then, yeah, I've had some, downturns in my career and various problems, but there was, in fact, all those kind of problems turned into something even better. Is kind of amazing. Various times in my career, and always be on the lookout for what may be a new direction for research, even if what's happening right now isn't working out. But yeah, it's hard to be a researcher, and it can be emotionally very difficult for you at times. But in the end, the thrill of doing science, the thrill of discovery, the thrill of writing a paper or giving a talk for the first time is just so fantastic. All that is quite worth it. So that's a good question. In fact, that's kind of the environment we're trying to create in my own company. And I think what happens is we have very clear goals of what the company is doing, and they're a lot more business goal than the typical scientific goal, but it's similar enough. And make sure that I and the other leaders have good goals and whatever, but we're giving all the people in us time and effort to be creative. And if they have an idea, maybe I'm not 100% thinking that will work, but as long as it doesn't take too much time and it can be done in an efficient way, then it's great. Let's see if it works. And I would say in my career, a lot of times I've been single-mindedly focused. Basically, I'm building a quantum computer. We do it this way. I've several times missed out on some good opportunities, but fortunately, other people in the field have done it, and you just take it over. But I want to make sure everyone in our group understands that. But we talk a lot about how to be creative, and there's this concept of that Alan Holm, my CEO, talks about that he learned from Amazon, having to do with one-way doors and two-way doors. And the basic idea here is sometimes you make a decision where once you make that decision, you're just stuck with it and you can't go back. And that happens all the time in experimental physics. You want to buy a really expensive piece of equipment or go in a certain direction. I mean, you're just stuck with that. But a lot of times it's something called a two-way door where you can go through and try it, but then you can come back and go back to whatever you were doing on before. And the important thing is to have a discussion with your employees. Is this a one-way door or a two-way door? And make sure we all understand the risks and reward and exactly what's going to happen as you proceed with that idea. Well, first of all, I'm married to a very wonderful person who will insist on the work-life balance. When I was young, especially in grad school, I did a lot of rock climbing. I actually donated a climbing guide to Yosemite Tuolumne Meadows as part of that. And I found that when I went on the climbing weekend and just focused on doing that, I forgot all about physics because it's a very intense sport. And I came back very refreshed and the like. What I do nowadays is hard for me to go climbing. I take a lot of long hikes. And I find this to be actually a creative time for me. I think I'm on the runner's high where you feel good about everything. But after I go home and I think about it, I reject about half my ideas because they were not necessarily good ideas. But yeah, I enjoy hiking. I enjoy dancing. We take a dance class with my wife. We go to church on Sunday. We try to do things together that doesn't involve physics. But I like physics a lot, so I spend a lot of time doing it still. Having other hobbies and focusing on that is quite good. And I think I tend to be very intense about doing the physics. So, having some other outlets. And I would say, especially as I get older, I need more downtime or rest time that I used to. The one thing that I am most interested in is using quantum computers for solving quantum chemistry and quantum materials problems. And this might be by developing a big database of chemical reactions and the like, which you can then use with AI to kind of develop new processes. But for example, if you can develop a new process using a quantum computer that's, say, cheaper or uses simpler materials, gets rid of various rare earth materials, things like that, be more ecologically sound, that can have a huge benefit to humanity that I'm kind of excited about happening. Because around us, nature is quantum in many of its properties. And if we can harness a quantum computer to solve those problems better, I think we can make a big impact. I still hear people say that this quantum mechanics is the physics of the microscopic, of the small, how atoms work, how molecules work, how fundamental particles work. And that's true, and that's how it was developed. But we showed that quantum mechanics is actually much more broader phenomenon than that. You can make electrical circuits that are this big, and we've showed that obeys quantum mechanics to it. Other people had looked at mechanical systems or magnetic systems and shown that this macroscopic quantum phenomenon is possible. So let's say the toolbox right now, you think about atoms and molecules, well, it's expanded into electrical circuits and mechanical circuits and other things like that. And because of that, we can build much more expansive or interesting quantum systems that we could have done 40 years ago. And a big application of that, of course, is the quantum computer. But people are also using making quantum devices, which are used which are similar principles and are used for doing astronomy applications. And for example, Ben Mazin, a professor at UC Santa Barbara, is using these kind of devices to look at exoplanets in astronomy and using some of their unique capabilities to build these new instruments. In fact, I spent part of my career doing that. So I'm really excited to see what's happened in the last 40 years, developing this technology for scientific instrumentation and hopefully eventually a quantum computer.